Hello, everyone. Good morning, good afternoon, good evening, wherever you happen to be joining us from. So I'm so glad that you could all join us here today. I am Eli Leland, CTO and co-founder at Voltaic, and I'd like to welcome you to our webinar on the topic of what battery manufacturing can learn from semiconductors. As we'll discuss, there are a lot of parallels that we can learn from to help battery manufacturing scale faster. And our guest today, Mark Willey, is the ideal guest to help us illuminate some of these opportunities. But first, I'll go through a couple of housekeeping notes. Following these introductory remarks, our guest will walk through a few slides to set the stage for today's topic. And after that, Mark and I will have an open conversation followed by an interactive audience Q&A session. Please submit your questions through the Q&A function of your Zoom app. You'll notice that the participant chat is disabled for this webinar. That's on purpose. There's nothing wrong. So please do use the Q&A function, which on my screen is at the bottom. I'm sure you'll be able to find it, and we look forward to some engaging questions from the audience. So now I'd like to properly introduce our guest. Mark Willey is the Senior Vice President of Customer Success and Partnerships here at Voltaic. Mark received a Ph.D. in Chemical Engineering from Columbia University, after which he spent over a decade in the semiconductor materials and manufacturing space, first at a company called Novellus, which was later acquired by Lam Research, and then at Moses Lake Industries. At Moses Lake, Mark recognized an opportunity for the company to move into batteries, and so he started and for 3 years led a battery materials division at MLI. After that, Mark went to work at Pacific Northwest National Laboratory, PNNL, where he worked to help accelerate the growth of the domestic battery supply chain. So here at Voltaic, we were thrilled to welcome Mark to the team earlier this year as our work in battery manufacturing continues to grow rapidly. And so we thought it'd be valuable for Mark to share some insights he's gathered over his career spanning semiconductor and battery manufacturing for our webinar discussion here today. So welcome, everyone. Welcome, Mark. So glad you could all join us. And now I will turn it over to Mark for his slide presentation.
Great. Thanks, Eli. Appreciate the intro. I'll have to steal that from my other intros of myself here. Okay, yeah, it's great to be here. We're going to spend today talking about manufacturing, mostly as a comparison between semiconductor and batteries. And the topic is, as Eli said, what battery manufacturing can learn from the semiconductor industry. So the first thing I want to do with this presentation is really kind of set it up through a historical perspective and look back in the semiconductor industry and what was going on in the 70s and 90s, and actually through the 2000s, to be honest, and see how there is, to be honest, a nice comparison of what's going on now with the battery manufacturing and ramping of that in the US. And specifically, we're going to look at Japan versus America. So right now, we're in this kind of China versus America mentality with batteries. But in the 70s and 90s, it was the US and Japan that were kind of ramping chip manufacturing and having these issues in the market. So let's look at that. So in this slide really showcases the issues, or I should say the market in general between the 50s and 2000s. The first thing that I'll call to attention here is the world semiconductor market graph that I'm showing here. You can see in this graph, it was really in the late 70s, early 80s that we started to see that inflection point in the chip manufacturing. And that really is kind of where we are today, right, in the battery world. And so looking at that, it's a good thing to kind of, check out this time frame. Also, the other thing that was going on besides that comparison was that you had Japan coming into the market in the mid 70s to late 70s, where they really had this push of their prowess in manufacturing, and specifically in memory chip manufacturing. And you can see from the graph here with the DRAM market share, Japan actually overtook the US in terms of chip manufacturing and sales in '82 for DRAM. And so this kind of comparison where they've grown and the U.S. actually shrunk, these kind of trade, this trade competition is very similar to what we're seeing today in terms of the battery industry with the U.S. and China. So the main points here is we have a market that looks similar in terms of its growth point trajectory. We've also got this competition between the U.S. and Japan. The key points also that I want to make is not only was the market growing, but you actually also had a lot of Japanese government interaction with the market. And so that's very similar to what the Chinese obviously have done over the last 10 to 20 years in the battery market, where they've invested heavily in Chinese companies in the space, not only in the actual manufacturing of batteries, but all throughout the supply chain. You also had a consortium actually built up in Japan that was actually some of the top companies there at the time making memory chips and other chips. And so a lot of these things are also happening in the battery market with the Chinese government. So that's to kind of set the stage. So we have kind of a similar, to be honest, a similar thing going on now, as I've mentioned, with the US and China. And the question really, the question we want to ask today, or the question we want to look at is, okay, we know this happened in the 70s and 80s and 90s with Japan and America. How did America actually get back in the game? Because we know in the 2000s, America actually had a very strong push in logic manufacturing and was able to actually get back into it. So I'm going to set this up a little bit in the next few slides, and then we're going to go really into specifics in the second half of the presentation. One of the main things that happened in semiconductor in the 80s was that there was a big push to go from just research and development investment actually into manufacturing process investment. So in the early days, in the semiconductor manufacturing world, like in the 50s and 60s, a lot of the investment was in research and development and was actually targeted at niche areas for the Defense Department and other different markets or smaller markets. And again, this is another very key similarity between the battery industry and the semiconductor industry is that that's really where a lot of the smaller companies in the US started in terms of battery manufacturing, was they were looking at these niche areas and supporting them before the electric vehicle revolution came. In the semiconductor side, it was really the same thing until the really big push in consumer electronics, right, in the 80s. You had a huge demand increase for consumer electronics throughout the 80s, 90s, and even through today. So what happened was that, and coming back to the initial point I was trying to make here, is that initially US was investing heavily in research and development in semiconductors. And what happened was that we lost the edge in terms of the process development to Japan. In Japan, they were really focused on not just R&D, but actually developing processes to increase yield in their manufacturing lines, which, as everybody knows, yield increase means lower cost. So they were able to actually have a lower cost, in this case, I'll just mention memory, than what we had in the US companies. And they were able to come into our market and actually significantly take over the market share. So what we did in the US, and this is just an article from Intel, was that we started to shift from a R&D development perspective in terms of investment into a manufacturing investment. The second thing that happened, and this is kind of similar to the first point, but I'm going to just delve into this a little bit more on the quality side, was not only in terms of process development investment, there was a heavy push for quality control throughout the supply chain and also in the actual chip fabs that were being brought up. So not only were the people investing in the process development, but actually in the quality control. The graph here on the right is actually another graph from Intel, and I love this graph because it shows the three kind of different cycles, or sorry, three different yield places where yield is being improved. Initially, we have the development of the chips. You can see the yield is lower here, and then it increases to a certain point. And then at that point, the actual chip is then pushed over to other fabs where they can actually produce at higher volume. So this is a common thing in semiconductors. You start out with like a development or small production fab that's a small one, development one, and you move into, once you get to a certain yield point, you actually release the process to these other fabs that are production fabs. The big point here is that you'll see the yield when the process is pushed to these other fabs is almost the same as in the development fab. Not only that, but the two fabs together, all three of the fabs, as you continue to see them over the years, they all kind of show that same trajectory. The point here is that the transfer of the process is very, in terms of yield, is very close. So this is something that we need to strive for, obviously, in the current battery industry, where transfer of these different transfer of the actual production of batteries in the development factories is not one-to-one with what we're seeing in the production factories. And this is really a result of the copy exact methodology that Intel implemented in their process development. The third thing that happened was the government. So the U.S. government actually intervened in this I'll call it a trade war, but this trade interaction between the U.S. and Japan. At the time, most of the consumer electronics were being manufactured in Japan, and then so the chip makers in Japan had a direct supply into those consumer electronics companies, and the U.S. is actually pretty much not able to access that market. And so the other thing that happened is that the investments that the Japanese government made to the Japanese companies was allowing them, along with their higher yields, was allowing these chip manufacturers into Japan to actually dump or reduce the price way below what the U.S. companies could do, and actually was able to displace obviously with the lower pricing, was able to displace a lot of the U.S. companies. So the U.S. government came in and basically negotiated with Japan and was able to get access to the Japanese market. So one of the key points here is in '86, this 20% market share was allowed for Americans to come into that market. And the second thing was simply to mitigate this dumping of memory. Really, this all comes down to what the U.S. was really pushing for level playing field. That same mentality right now is coming into play with the US and China. We're trying to get a level playing field for how we produce chips in the US, how we produce batteries across the world. We want to make sure that the competition is fair. In the next section here, with this setup, I'm really going to just drive on discussing, okay, what can we learn from these things in the semiconductor industry now, but specifically not on the government side. I'll stay on the actual manufacturing side. And I'm specifically going to stay in the upstream side of it. So right before the materials and all this equipment gets into the actual fabs, and what was done to actually increase yields in that perspective. In some of the later seminars that we'll probably be holding, we're going to really focus on that latter part of inside the factories, how we improve yields. Okay, so let's talk about how we get these increased yields. And like I said, I'm going to focus on the supply chain quality control on the upstream side. One of the main points I want to make here, and one of the challenges we have in the battery industry, is that getting higher yields is all about trust between each of the players within the supply chain. When you have a end user, a OEM making an actual product, if they have strong trust with the partners in their supply chain, they're able to have those partners share lots of data across the supply chain and understand how the quality changes, how the process changes in the upstream side of the supply chain affect the quality of the batteries or of the semiconductor chips that they're making. The key here is that just like in the battery field, in semiconductor, the chip manufacturers don't know what affects the yield in the upstream, what affect the upstream small changes in pumps, in materials purity, in all these different things. They don't understand at the beginning how that affects the yield when you get up to higher percentages of yield above 90%. So small changes in the upstream side, if they're actually identified and shown to the chip maker, then they can actually see how they affect their the finished good of the chip. So again, some ways that the semiconductor industry has been able to achieve this good yield is really through this trust throughout the supply chain. And that really means that the chip makers are able to have their suppliers adhere to a few things that I call out down here. And I'll go through, in the next few slides, I'm actually going to go through and call out and talk in more detail about a few of them. One of the first things is ship to control. And not specification. Right now, a lot of the manufacturers in the battery space are still relying on just looking at the specs of incoming materials and saying, yes, that's good. We'll bring it into the factory for us to produce our batteries. We'll go into more detail of how that can be a problem as the yields become higher. When you have a sub-supplier go out of business, or you lose a supply chain piece and you're in the puzzle of the supply chain, and you need to actually bring on a new material, fingerprinting is a key thing. So you need to be able to fingerprint, and we'll go into detail on this in a subsequent slide, but fingerprinting and analysis of these materials and just of the equipment that you're bringing into the factories is key to understand at depth if I make a change in my supplier, that it's not going to affect my yield. Change control, again, you don't know what you don't know. So if somebody changes a pump or a tank in the upstream side of your supply chain, maybe that wasn't on your spec, but how does that affect your yield? Well, in most cases, it does. And you need to have strict change control so that your vendors, before the chip or the battery is manufactured, notify you of a change or actually go through some process to qualify that change. Data transparency, I talked about a little bit. Again, this is this trust between all these different players in the supply chain leading up to the manufacturing of the battery or the chip. If the factory making the chip can actually see all the data that leads up to the actual use of that material or equipment in the factory, if they can see all that data and they see a problem in their chip manufacturing, they can then use that data to go do a root cause analysis and then improve the supply chain behind them. And the other thing is, the fifth point here is really this trust and this relationship in the semiconductor industry right now allows for the chip makers to actually disseminate the information on best practices for quality control and what is really needed at the sub-supplier and supplier level to achieve high yields. So there's this back and forth discussion. It's not just a business, a strict business here, I ship you this material, you accept it. It's actually a discussion where the quality teams on both sides get together and discuss the best practices of what needs to be done to make the yield at the chip or battery manufacturer better. Okay, so let's dig into ship to control. So I'm gonna just actually point out a few of these things that I just talked about. One of the biggest things in terms of increasing yield as you get up again above 90% is this idea of ship to control. For those of you that are not familiar with this, this is really a methodology of determining control limits of normal process variation. So on the left here, this is an example of I believe it's a metal target that a company is using for their processing of chips. Basically, what this is showing is the oxygen content in that target. So this is a titanium target, I believe. It's showing the variation in the production of that target. And what you can see here is that at some point, the process goes above normal variation, and you see it go out of what we call out of control. If the chip maker was simply relying on the initial specification limits that it supplied to the upstream supplier, this would not flag anything. Now, we have to remember that the specifications are usually done at the beginning of the process before the yields get to the point where they're sensitive to all these small changes. So the point being is that we set the specification limit. This variation wasn't accounted for. We didn't see yield problems at that point, or we probably did, we just weren't looking at it. And now, as the yield is up in the higher 90% at the chip maker, now all of a sudden we see this out of control, this oxygen, which actually now affects our yield. If we didn't have this ship to control set up, we wouldn't know what the problem was. So the key here is we have to go, in the battery industry, we have to go beyond this ship to spec and go into this ship to control so that we understand how all the variations in the upstream materials affect the actual yield of the batteries coming out of the factories. Fingerprinting is another thing that is done heavily in the semiconductor industry, and I'll go into the detail of what that really means. But in this slide, really what it means is that when you actually have a material, you don't just look at and analyze the spec of that material initially. You actually go through and fingerprint the material beyond the parameters that are on a spec. I always say that this is really when I was in my previous life working with these big semiconductor manufacturers, they would come to us and basically ask for every analytical method that we could apply to that material to actually get a fingerprint of it, so that if something happened in the future and we had to make a change in our supply chain of raw materials coming into our factory as a supplier, that we had this fingerprint to actually go and look at to make sure that the sub-suppliers were adhering to that same, that the material from the sub-suppliers looked the same. So again, so what happens, hopefully not too often, but does happen in the production of materials to a chip maker is that the upstream supply chains often get disrupted. So you might have a raw material, might be some petroleum material or some polymer that you're using or some small molecule you're using for making your finished good. I just showed 2 raw material suppliers here. This is usually on the order of, probably 10 different suppliers you're bringing in just to make your finished good, which is going to the chip maker for one small, tiny part of their process. Now, if my raw material supplier A goes out of business or has some kind of business continuity problem, a tornado goes across their plant, labor force issue, they have to shut down. All of a sudden, we obviously, most companies have backup plans in terms of stockpiles, but let's assume that you get to the point of the stockpiles run out, you have to switch suppliers. You're now forced to actually bring in a raw material supplier B that has not been qualified by the chip maker. So again, usually what you'll do is when you start up with producing materials for a chip maker is you go through a qualification. That qualification then fingerprints all the upstream manufacturing path. If you interrupt that manufacturing path, the chip maker has never seen that material from raw material supplier B. So what we have to do is in order for them to reduce their risk, and not, because again, they haven't seen the material or qualified it at the chip maker side, we have to go through and look at the fingerprint that we've already made on the original supplier A material. So this fingerprinting, it seems very simple, I guess, but it's actually a key thing for reducing your business continuity, your risk in supply chain issues. So again, it's usually used as a last effort. You really want to have multiple qualified suppliers that have been qualified. But this method helps when you actually run into the situation of you have to qualify a new vendor during the production of these chips. We're going to talk a little bit of end-of-line testing. Obviously, in the battery side, we're very involved. Voltaic is very involved in end-of-line testing, and I think it's very important to understand in the industry right now, in the battery industry, there's a lot of sampling testing that's done in terms of pulling samples off the battery lines and testing them. And it's very important, I think, to understand how the semiconductor industry does end-of-line testing, which is I would say much more rigorous right now than what's happening in the battery side. I think one of the big things is every chip on a wafer that's coming out is tested. Okay, that's something that we cannot say in the battery industry right now. And there's a lot of people say that, there's a lot of comments that are, well, we can never test every battery. Well, and we'll get into that, but really the answer is you actually, during formation of these batteries, you have a test that's already going on. And so there's a lot of data on that testing that can already be pulled off and analyzed for quality control. So I'll leave that there for a second. We'll probably get back to that in the discussions later. But one thing I want to make a point of is there's these different tests at end of line on the chips. One of these is functional testing, one is parametric testing, and one is reliability testing. So not only are you testing the functionality, okay, does the actual functions on these chips respond correctly? You're testing for voltage and current, frequency monitoring, some other operating conditions in terms of temperatures, the chip operating correctly at these different temperatures. You also do long-term reliability testing. So this can be considered in the battery field. We pull samples often from the lines to actually do these long-term cycling tests. This reliability test could be thought of as the same thing. They do these with different humidity and temperatures, voltages on these chips to make sure they're good. The thing that this also allows, beyond just being able to understand or to make sure you're not shipping chips that are bad, is it allows you to, when you find a problem on a chip, you can actually go back and do a root cause analysis upstream in the supply chain for that chip or in the factory itself. So this allows you to really quickly adjust your process and have that feedback loop to continually adjust the process or the supply chain to increase the yield. Again, this is something we need to strive for in the battery industry. We need to start taking all this data off the end of the line and actually analyzing it so that we can not only not ship bad batteries that cause fires or these other problems, but actually go back and improve our processes for our company as a battery maker and increase the yields and therefore reduce the costs. The last thing I'm going to talk about here is change control. One of the things that, again, this comes back to kind of the initial discussions I was mentioning before in terms of shift to control, is that the chip makers don't know what they don't know. So they don't know if you buy a pump 1 year and you put it in and then it dies, if you replace that pump with what you think is exact, and you start producing material that's then shipped to the chip maker, they don't know that you've changed that pump, but maybe they're seeing reduction in yield. And now they can't figure out why we haven't seen any issue upstream, no changes that were notified to them upstream. Why is there a problem with my yield? Well, it turns out that pump was actually using, instead of a Teflon material, was maybe using a Viton material. And even though the actual manufacturing method being used for the material didn't seem to change in terms of what we're measuring, the actual yield at the chip maker actually caused a problem. So because of that risk, okay, again, this all comes down to reduction in risk of the chip maker in the upstream. Because of that risk, the semiconductor industry upholds the change control, which means that each supplier, and for robust supply chains, this means sub-suppliers and sub-suppliers, sub-suppliers, are notifying the different parts of the supply chain that there are changes happening. So this allows for, and not only that, but it allows for the chip maker to address and say, oh yeah, that we think that's going to actually impact our chip manufacturing process. Let's go through a qualification of that change. Sometimes the chip maker will actually just say, no, we don't need to go through qualification. That costs a lot of money. We will just actually accept the material as long as you do rigorous testing on the change in terms of metrology, that kind of thing, analytics. But the main point here is that they're notified. I think that, just making sure that they actually see that there is a change happening on the upstream side, so that when they start to see something happening with their yield, they can at least go back and say, oh, there was a change that happened and we need to go and address this. And I was incorrect, actually. I'm going to talk about one more thing, so I'll keep on talking for a few more minutes on this. But and this really feeds into this whole discussion of trust throughout, again, this whole overarching, I guess, message I'm trying to give, which is that in the battery industry, we need to develop this trust throughout the supply chain. And one of the reasons we need to do that is to be able to get all this data throughout the different parts of the manufacturing process leading up to the chip maker, so that when an issue happens with when an issue happens upstream, the chip maker is actually able to correlate that to the end of line yield that they're seeing. Again, the big point here is that the only person who really knows the impact of the upstream manufacturing, this isn't totally exactly correct, but in general, the only person or the people that have the knowledge of how the yield is changing is the chip manufacturer. Oftentimes, obviously, that information is passed back down through the supply chain so that other people know. But the key thing here is that for each step in a manufactured material, in this case, the quality data coming off these different parts is then fed to the upstream upstream purchasing partner. And so in the case here, we have raw material company A, they're selling their raw material to raw material company G, and that quality data is going through an incoming quality analysis. And so it's not just that they're sending the material with a spec or a certificate of analysis. There's actually a review either of the certificate of analysis, or there's another analysis at this raw material company G that's going on to actually look and say, does that material look the same as when you shipped it out as when I accepted it? Now, if you go beyond that, as I discussed right at the beginning of this slide, if you go beyond that, and just imagine if the quality data from each of these steps was given to the chip manufacturer, the power of having all that data throughout the supply chain and the knowledge of seeing and being able to look at all those control charts of these different parameters throughout the supply chain allows the chip manufacturer to then address changes in yield and go back and basically do a root cause of why did my yield change, because now I have all this quality data. What does this require? One of the biggest things, again, is trust between the chip maker and its upstream supply chain. That is something we struggle with right now on the battery side, and mainly because of this kind of the geopolitical wars that are going on right now. If you look at a battery manufacturer within the United States, where are they getting most of the materials from? It's not from the United States right now. And so the material suppliers actually have the strength in the relationship, and even the tool suppliers have the strength in the relationship, which means that if the battery manufacturer says, hey, I need to know all this information upstream, the material supplier is going to say, look, take it or leave it. And a lot of times right now, we have to take it because we don't have another place to get it from. And so this, again, as the industry moves forward, as the supply chain actually builds up, I believe that we will see the same thing that happened in semiconductor, where the strength moves back into the actual OEM side or the or battery manufacturing side, and these better control things that I've talked about are going to be pushed upstream throughout the supply chain. Ideally, we could do this immediately, but obviously there's these different pushes and pulls in the business relationships. With that, I'm just going to summarize. Again, this is really just a summary of what I've already said in the previous slides of what we can learn from the semiconductor side and apply it to the battery side. We need to move to shift to control as much as possible. We need stringent characterization of materials and equipment, obviously in fingerprinting the material or just how the equipment's actually operating, so that when something goes wrong in the supply chain, we have another place to get that piece of equipment or material. We need change control. Again, the battery manufacturers don't know if a change upstream in a pump or a tank would cause an issue until they see a problem with their yield. So we need to make sure the upstream side of the supply chain is actually notifying the later parts of the supply chain that there's a change. We need data transparency in the quality data. The more data given to the end of the line in terms of the battery manufacturers, the better they're going to be able to see what caused the problem upstream and make better batteries and have higher yields, lower cost. We need collaboration again, this relies on collaboration between the supply chain at all stages. And we need to leverage the full potential of the end-of-line testing. Again, we have so many batteries being manufactured going through this formation step, again, where there's a lot of this voltage and current data that's just being ignored right now. We need to use all that information and again, apply it so that we can actually find these problems and use that as a quality metric, then go chase down the problem in the upstream side or in the manufacturing plant that we're making the batteries. So with that, I am going to end now, and we're going to go through a little discussion. Eli's going to come back on here.
Awesome. Thanks so much, Mark. You're welcome to stop sharing your slides so everyone can see us full size. Excellent. So you lay out a lot of ambitious, I would say, sort of dynamics and relationships that yet need to be developed in the battery sector. I'm sure for a lot of people listening, it might sound a little bit pie in the sky, but I would suspect that, looking, say, if you were in 1983 instead of 2023, people in semiconductors might have said similar things, and now we've got this super advanced and sophisticated global industry. That was sort of the last great platform technology and hardware technology, whereas we see batteries as kind of the next one. So it's really exciting to see these things coming together. I'd love to just hear a little bit more about your story, Mark. Whereas you had spent, a decade, give or take, in semi, and you were at Moses Lake, which was a material supplier into the semiconductor industry. So you were very much face to face with all those quality practices for the large semiconductor manufacturers required of their suppliers. But what was the opportunity that you recognized at Moses Lake to get into the battery sector? And I'd love to just hear a little bit more about that part of your journey.
Yeah, sure. Yeah, so when I was at Moses Lake around 2015, actually, we started interacting actually at Moses Lake through Intel. Actually, we were interacted with a different battery manufacturer, and at that time we were focused on, on a different piece of the battery that was not a material. Actually, I think it was the anode that we were working on. But at that point, in that interaction that we were kind of pushed into, I'd like to say that I was just fully on, pushing this new portfolio of battery materials. But during that interaction with the battery company, we realized that, there's not a lot of people in the industry right now manufacturing in the US materials for batteries. And I just thought, man, this is a huge gap. And as I started to look around, and as I started to play around with numbers, it just was astounding, actually, even in obviously much more so in 2015 than now, the lack of a materials environment for, again, at that time in 2015, a lot of the smaller cell manufacturers to get materials from. So that's why we pushed into that. We started with electrolytes, and then we also did some binder work and some other polymer materials. So we had a lot of synergies, and this is another thing actually we can bring up, which is that in the semiconductor side, the material side, we were in this electrodeposition product side. So it was actually a lot of the same principles that go into battery materials and use. We at Moses Lake Industry, we had a lot of those same people. We had electrochemists, we had chemists, we had analytics people. We could use all of those capabilities, and we could apply them to this other market that was the batteries market. And there was no other company, not no other companies. There was very few companies in the U.S. that were actually supplying materials. So the build in America, the actual core capabilities of the company, all pushed us into that. Plus, just developing a larger portfolio of different markets, as everybody knows. Well, maybe people don't know, but the semiconductor market is a cyclical market. So in down years in the semiconductor market, you want to have some other part of your product portfolio that can, basically buffer that low revenue at that point. So all those things kind of led to us pushing into that side.
Awesome. So following Moses Lake, you moved on to PNNL, where I know you were studying the domestic battery supply chain.
Yep.
And so I'm interested to hear a little bit more about that work and what you found and observed as the primary challenges to scaling up a US-based domestic battery supply chain and battery materials supply chain. What are the key barriers there?
Yeah, I mean, it all comes down to, it's all money. So I think it's all money, and I think it's also an understanding of where the materials are coming from and the environmental impact of where those materials are coming from. So what I learned, from coming from MLI, I had a very good sense of the market. I would say, since I developed, we went through and did a full business case and analyzed competition throughout the world. I think the main thing is obviously a lot of the materials are coming from China. You had some Korean and Japanese companies also in the material industry. Very few materials companies competing in the U.S. And the reason is that they just couldn't compete at the price points that these other companies were selling at. With that said, as we become more conscious of, okay, how are these materials made? What is the carbon footprint? What are they doing to the environment in terms of mining? What we found, is that, well, what we see right now is that instead of just a price point for buying a car or a battery, the market now is much more sensitive to, and it's good that this is the case, is much more sensitive to what is the environmental impact of me purchasing this finished good from again, it could be a consumer electronic that uses the battery, or it could be a car. And so that was one of the things that, then what that led to is that the government also saw that, obviously, as well, with all these restrictions on, making sure, the easy case is making sure that we're not buying conflict minerals like cobalt from mines that are using child labor. Again, this transparency throughout the supply chain on the end, people, the common people buying these products, just even having that sense of, okay, I need to make sure that this material was not made with, a conflict mineral. That was one of the big things that's really, I would say, come to light over the last few years for me, and that has enabled us in the U.S. to really, we need to push that. We need to push the fact that manufacturing can come back to the U.S. We just need to be smarter about how we're actually manufacturing in terms of this environmental footprint. And we need to make sure the public is aware that when we when these batteries are made with some of these foreign entities, we need to make sure that everybody's aware of how they're made. And I heard a talk from, I forgot who it was, but I thought there was a really good quote in this talk, which basically said, the American public is really offshored its responsibility for the environment. We use all these things. We just don't want to see it made in America because we don't want to see the impact it has on the environment. We need to get away from that and actually think globally in terms of the impact. And what that really means is the US actually is the best place to be making materials and equipment, because we have the restrictions on environmental manufacturing. We have this oversight that can reduce the greenhouse gas issues. So I kind of went on a tangent there. I kind of wandered around. I know, so I apologize for that, but I wanted to make sure I got a few of those things out.
Sure. No, that's great. And I think, talking about trust, transparency, all those things, that sort of leads into my next question. So both in your slides and in the little meandering path that you just took us along, you spoke about the importance of trust and transparency across the supply chain. So that makes a lot of intuitive sense, but in practice, that sounds like it's probably something that can take several years to develop at a minimum. Do you have any thoughts on how to accelerate this process, especially as we're in this critical period where the battery industry is, the demand is spiking and we're all of the production and supply chain seems to be lagging a couple of years behind. It's vital that we accelerate this. So in terms of that relationship dynamic.
Yeah. Well, I think you're already seeing, so I think Tesla already did it immediately, right? So I think the main thing is vertical integration. If you can't rely on your suppliers to actually interact properly, or I should say properly, in the way that you want them to, in terms of transferring data and all these other quality parameters that you'd want, and actually securing supply chains, you go to a vertical supply chain integration. So you have Tesla started doing this a while ago. You saw everybody else in the car industry seem to follow suit in terms of GM, the big three in the US, and a lot of the other car companies. So what's happening is that they're really pushing this all. They're actually buying up these companies and investing in all these different parts of the supply chain to make sure that they do have that control. And so that is, I think it really is accelerating it. There's only so, I think the issue you have is that there's only so, you can only do things so quickly in terms of making a factory. And so that's where we're stumbling right now, is like, I think the direction is the correct one, which is this vertical integration. I think the challenge is that you can't build these things, or you can't design, build, and do all these things in a year. They take time, oftentimes 5 to 10 years to actually build a factory, qualify materials, and make sure that they're operating correctly.
Yeah, and we've certainly seen, if folks have seen other material of ours, we cite, contemporary examples where it's taking even some of the biggest and best battery manufacturers in the world. It's taking them, on the order of 4 or 5 years to ramp up their new gigafactories to full production. So that's really the name of the game, and that's why we're having this conversation. And it's a work we do every day, is to try and help accelerate this. I want to dig in a little bit more on.
Oh,
go ahead.
Let me say one other thing, which I just thought of, and
yeah.
I think it's important to mention, which is there needs to be a lot more transparency also to the American public about bringing manufacturing back, and these restrictions on permitting and all this, the time it takes to permit and all this stuff. I think we do in the US need to get past this not in my backyard mentality, as I mentioned, this kind of global thought of manufacturing. And we need to make sure people understand it's not the 1950s, or I would say 1920s, in terms of making oil and mining. We have the 2020s technology to do all these processes that were before done very in a dirty fashion. We can now do them really clean. And so I think we need to make sure, and that's a responsibility on the manufacturing side, is we need to make sure the American public understands that, and we need to get that information out and make sure that we tell people this is not the 50s kind of technology we're going to use. Sorry.
Indeed. Yeah, no, engaging the public trust is going to be a very important part of this energy transition overall. So want to dig in a little bit on one of the more technical topics you covered in your slide in terms of end-of-line testing. You suggested that there's some low-hanging fruit there that, we maybe need to kind of reframe how we're thinking about formation cycling at the end of manufacturing for lithium-ion batteries as an opportunity to do more with that data, end-of-line testing. Can you speak more to that?
Sure. So obviously, I think most people know that every battery that is made goes through a formation. The actual creation of the battery is this formation, this electrochemical step. Now, during this step, there's this obviously a current or voltage or multiple current and voltage kind of steps and waveforms that are used to make it. There's a lot of information in that formation step in terms of voltage and current curves, and then analysis on top of them that can be used for quality control. So if we were able to pull off all that data from the formation cycles, and oftentimes I'll also mention that there's also a performance test that's done really quickly after. There might be some pulsing done just quickly just to check resistances or different parameters. But if we were able to take every battery's information and then use that to do quality control, that would be a key thing. You would actually be able to determine, you'd be able to one, make sure you don't ship out bad batteries, and two, you'd be able to go figure out what the problem is in the upstream, whether it's in the factory yourself, at your own manufacturing site, or if it's in the upstream side. So that capability is key. And I think when I hear people say, oh, this isn't the semiconductor industry, we can't test everything, we can't look at everything, we've got too many batteries coming out. I think, geez, you already have the data. We can at least use that data that we have in the formation. It's just the ability to take that vast amount of data, pull off quality metrics, and then translate that into a system of quality control is what is needed now.
Excellent. So yeah, I want to go just one level deeper there. So you also talked in your slides about how semi, they can use that end-of-line testing to diagnose materials or process problems in their upstream supply chain, not just in their own facility. Right. So how do they do that? If basically you're looking at a chip that's coming off the end of the line and you're able to diagnose something that happened before the materials even got into your facility, how do they do that in semi, and how might that translate to batteries with the example of the formation cycling analysis that you just mentioned?
Yeah, well, we talked about end of line, but to be honest, there's a ton of testing throughout the manufacturing process where you catch stuff in these different subsequent steps. So each, you can think of a fab or a chip manufacturer just as like a car production, like Ford's car production line where there's different steps. Each step is a tool, and there's analysis done on each tool. And so usually the way that this happens is there's a failure on an analysis, let's say during etch. Maybe there's an etch problem. Now the etch looks, the characteristics looks bad, and that they know, from their massive amounts of knowledge, they know if the etch profile looks like that, it's going to cause a problem. At that point, they would then go and start this quality assessment. Again, it becomes an escalation. It goes through a whole escalation team. There's a quality team that then is really reaching back up through again, these are large teams of quality engineers that are going and looking through the supply chain for the problem with the etch. Now, it could be the tool, could be the material, could be the environment, it could be many other things. So then all these teams are hitting all those different areas and going through it and analyzing it. And there's data that's being distributed from the suppliers all the way back to the chip maker for all those, for that root cause analysis.
Awesome. Well, it really is remarkable how many parallels there are. There's things that are quite different, whereas in semiconductors, you've got fundamentally a batch process at the wafer level, and in batteries, everything's moving towards, these continuous roll-to-roll processes. But so many lessons to be learned in terms of supply chain, metrology testing, in order to just maximize quality and really accelerate the industry. And again, it's exciting to be working with you and working with our customers on this, on these challenges. And we will definitely be doing more webinars on the broader topic of battery manufacturing over the next several months. So I think we've sort of teased a number of potential topics, and so we've gone deep on supply chain today. And in future webinars, we'll be going through things like process development, scale up of manufacturing, et cetera. But this has been a terrific conversation. So we thank everyone for joining us today. And now we've had some great activity in the Q&A section. And so we'll go on to a few audience questions. So I'll open it up with this one. Mark, can you speak to the differences between the CHIPS Act and the American Battery Materials Initiative? And also, is there an idea of the Asian? Do you have an idea of the Asian plant's yield? I presumably in batteries, and what are the main losses? And is it chemistry or cell format dependent? So I guess there's a couple questions in there: chips versus American batteries, and then the other ones are benchmarking yield at the Asian factories and failure modes and dependencies on chemistry and format. Let's start with the first: chips versus American battery materials.
Yeah, I think when you say America, I know the CHIPS Act, the American Battery. I think you're referring to the bipartisan infrastructure legislation, and then also the IRA. So I'll go into those two. Those are the ones that I'll just talk about those first.
Sure.
So yeah, so just and sorry, the question was, the similarities.
The differences between chips and the American Battery Materials Initiative is the form of the question, but you're welcome to answer in terms of IRA and infrastructure.
I mean, the money. I mean, so the amount of money the CHIPS Act has is ridiculous. I mean, in terms of how big it is compared to what the bill has. The IRA. So just to be clear, the IRA, and this is about a year ago that I was looking at this stuff, but the IRA was really more policy based, like trying to promote U.S. manufacturing through reduced or through incentives for people to actually buy U.S. made material or cars. The bipartisan infrastructure legislation actually had lump sums of money, and again, it was $7 billion, I believe, was the total amount. I think 3 or 4 of which have already been given out. But part of that $7 billion was really for building U.S. manufacturing. So really getting cathode, anode, and other upstream materials, silicon, graphite, getting all these materials manufacturers propped up. Again, this comes back to this level playing field discussion we had, which was, for somebody to get into the materials manufacturing business for batteries, just like I was in, if you want to do it at the volumes of millions of kgs of material, just think of the capital investment you have to make to do that. It's ridiculously large, huge risk, and guess what? The margins are really bad. They're in the percent or negative percent right now. And so a lot of these Asian companies actually are able to, if we take some of the larger Korean companies or Japanese companies, they're actually able to get in the market initially just through losing money because they can support it on a different part of their company. They can support the overall bottom line with maybe a consumer electronic they're selling as opposed to material, but they can support that 5 years of losses in the hundreds or millions of dollars range, and be able to supply materials to be able to eventually capture the money in 10 years. Okay, I wandered off there, but the bipartisan infrastructure legislation was specifically for that. The CHIPS bill, it seems like, and again, I'm sure everybody knows more about this than I do. I think the main things I've heard about the CHIPS bill is really this idea of building I think there's a consortium also idea of building this consortium to bring together for training and getting more people educated in semiconductor. There's also a lot of money that went into, I believe, supporting different fabs, for bringing chip manufacturing back into the U.S. So whereas the bill really focused on upstream, I would say the CHIPS Act that I know of was really focused more on like the Intels or Microns, or getting them to incentivize them to actually put the plants in the U.S. as opposed to having plants in Asia.
Great. Can you speak to the other parts of the question? Just benchmarking. I think presumably what we see in terms of the Asian battery manufacturing yields. I know we have some kind of anecdotal hearsay numbers.
Yeah, to be honest, I'm not the best one on this. I don't know the yield numbers that well. I think what I would say is that I do know from factory to factory in the battery industry, the yields are vastly different. So copy exact is not here right now. I'm not going to name the names of the manufacturers, but big battery manufacturers are setting up plants in different parts of the world, and they are coming online with vastly different yield percentages. I've heard everything from like literally 30% all the way up to 95% in terms of yields. The other thing that's happening is that those yield numbers are being manipulated. When we talk about yields, a lot of the companies will show high yields, but that's because they're taking the bad batteries and recycling them back into their lines, and then not accounting for that, so that yield loss. So you have to be, I'd say one thing you have to be careful of is how that yield number is calculated.
Interesting. Yeah, we've definitely heard those sort of gaming the numbers in terms of yield and where exactly what you're measuring, what your output and inputs are. So I'll ask another one that I swear this wasn't this wasn't a voltaic seed question. This is a genuine question from the audience. How do you think initiatives such as battery passport or battery digital twins might help to exploit all the data that is today generated through the battery manufacturing process?
The question is how we utilize that, or?
Yeah, how might battery? So I guess I'll sort of flip the question around. So how can we leverage the data that is generated during battery manufacturing toward initiatives like battery passport, battery digital twins? Like, so what do you envision as kind of the role of a full life cycle, data digital thread for a battery that might begin at the manufacturing plant or even, per your talk, upstream in terms of the supply chain?
Yeah, exactly. To be honest, there's basically the quality discussion I had, you could just put that right into your passport discussion. All that information, the quality data will give you all the passport information. So I think it's key. I also think that passport is key for, I mean, the reason we have it, right, is to understand where everything came from, how much was manufactured in the different parts of the world and where it was manufactured, what kind of environmental regulations were used during the manufacture of the material. I mean, we're in such a lucky, to be honest, a lucky position in the world today with the computing power and the ability, how cheap memory is in disk space. Now, I think we also have, you go back to 1980s. Imagine thinking about how much data, how much disk space cost in 85 or 86. You couldn't do. I mean, like, it would not be physically or cost. It would be such a huge cost burden that you would never be able to do what we can do today at such a low cost and understanding that full data transparency. So again, I know I meandered there. I think the key is that the passport is key. I think we have to have that. I think that is it's synergistic with the quality data. That full quality and passport information, that allows us to make not only cheaper batteries, but batteries that uphold to the environmental rules that we as a public want.
Awesome. Yes, and I know that that's a big part of battery passport, in particular. The forthcoming EU regulation is the environmental stewardship component, which of course we all take very seriously. Everyone who's engaged in this, helping to accelerate the energy transition. So with that, we're out of time. We've had a bunch of really fantastic questions in the Q&A that I'm sorry we didn't get to. I definitely invite the folks who had those questions to reach out to us. I am Eli, E-L-I, at voltaic.com. Mark is mark.willey at voltaic.com. You'll all get some follow-up emails with a link to a recording of today's session and a copy of the slides. So we look forward to future engagement. And again, keep your eyes on our feed on LinkedIn and elsewhere. We will be doing at least a few more of these battery manufacturing webinars in the coming months, and we look forward to seeing you there. Thanks so much, everybody, and thanks to Mark.
Yeah, thanks, everybody.